So this is the limit definition of the derivative. It is related to understanding how a secant line gets closer and closer to a tangent line as the 2 points the secant is going through get closer together. The distance between those points is represented by h. So in this part of the limit definition of the derivative, this is actually just representing the slope between the 2 points. So we know slope as the change in y over the change in x. That's what this is showing here as well. So this is saying some y value, because it's f of x plus h, so some y value where we've added h compared to this y value. So both of these are the y values of points on this function. One of them is a distance of h away from the other. In the denominator, we just have 2 x values, some x value and another x value that is a distance of h away from this one. If I were to simplify the denominator here, I don't actually need these parentheses anymore. And then I have x plus h minus h. Those x's are just going to cancel out. So in actuality, we think of this definition of having a denominator here of just h. Again, remember, h is representing the distance between the x values of 2 points on some function. So really, all this is telling us is we have 2 points. H is representing the distance between them. These are the 2 y values. And we're looking for the limit as h approaches 0, so as those 2 points are getting closer and closer together. Now visually, we talked about this like if I have a parabola, and let's say that I have a point here, and I'm trying to approximate what the slope is at this point. The slope at just a single point is called the instantaneous rate of change. To figure out what that is, we imagine that there's another point on this parabola. The secant line going through them looks like this. But if I take this point and I move it closer and closer to the point I'm actually interested in, as I get really, really close, that secant line is going to better represent the tangent line. So I'm imagining, what is this slope of this secant line approaching as the distance between these points goes away, as it approaches 0. Okay, so let's take an example of how we use the limit definition of the derivative. Let's say we have, we'll do a quadratic function. Let's say we have like 4x squared plus 5. Why not? So we're going to take this function. I'm going to substitute in x plus h first. Then I'll substitute in just x, which means it will look the same, and we will subtract those two to take care of this numerator. The reason we can't just start by plugging in h is because then we would get a denominator of 0, which would make this undefined. However, going through and actually applying this expression, like evaluating it at x plus h and also at x, I should end up having a bunch of things that cancel each other out and ending up with the ability to factor out an h so that I can simplify an h over an h. So let's see what that looks like. So I'm going to start by actually writing all of this out again, kind of, but plugging in the x plus h here. So 4 times x plus h squared plus 5. You might remember from class, I talked about how students frequently will forget to distribute the negative to the entire function. So I'm going to subtract, and as soon as I write that subtraction symbol, I'm going to start a bracket to remind myself that everything from this function is being subtracted. So we'll need to distribute this negative. So in here goes, it's just f of x, so it's just this expression here, 4x squared plus 5. all of this is still over h, and I'm still looking at the limit as h approaches 0. Okay, so let's think about this. X plus h squared, it is not x squared plus h squared. We have to think about doing x plus h times x plus h and distributing. When I actually distribute that out, I get x squared plus 2xh plus h squared plus 5. I'm going to go ahead and distribute this negative here as well. So minus 4x squared minus 5. This is still all over h. Okay, now I need to distribute my 4. So that's going to give me 4x squared plus 4 times 2 is 8xh plus 4h squared. I actually noticed that this plus 5 and minus 5, those just combine to give me 0, and then minus 4x squared. That is still all over h. But oh my goodness, I have another example of two terms that can cancel each other out, positive 4x squared and negative 4x squared. So let's just go ahead and erase those. Okay, so I'm still looking here for the limit as h approaches 0. And I notice that in my numerator, the two terms that remain both have an h in them. So I'm going to factor that out. So now we have the limit as h approaches 0 of h times 8x plus 4h over h. These h's cancel each other out. They simplify to just 1. So that means I'm left with, I'm running out of space. We're going to go up here. That means I'm left with the limit as h approaches 0 of 8x plus 4h. And now I can plug in 0 for h because I don't have an h in the denominator anymore, so it's not going to create something that's undefined. So this is equal to just 8x plus 4 times 0. That is just 0. So my answer is 8x. Now this should look familiar to us because now we've learned the power rule for derivatives. So we know that when I apply the power rule here, I would do 2 times 4, which gives me 8. And then x squared, I subtract 1 from the exponent, so it should be just x to the first, so 8x.